Today's topic is linear algebra and the subtopic is rank nullity theorem, or it is also known as Sylvester's law. And this theorem states that here T be a linear mapping from V to W. Both are the vector space over the same field F, and V must be a finite dimensional vector space. Then theorem states that dimension of MT plus dimension of T is equal to dimension of V. That is, rank of T plus nullity of T is equal to dimension of V. And we know that the dimension of MT is known as rank of T and dimension of T is known as nullity of T. Before going to the proof of this theorem, we define here two terms. First is MT. This is the set of T of V for all V belongs to V, and curl T is the element V belongs to V for which T of V is equal to theta, where theta is zero element of V. This is MT and this is T. To prove this theorem, we first let dimension of T is equal to M. So the basis of T consists M element. Here we let x1, x2 to xm be a basis of T. And since this is the basis of T, so it must be a subset of V. And it is the basis of T, so this set, if we name as S, this set must be linearly independent. Also, by extension theorem, we know that any linearly independent set of vector space must be extended to the basis of the vector space V. So, this set S is also extended to the basis of V. Let the extension be x1, x2 to xm, v1, v2 to vn, and this is a basis of V. Let here the dimension of V is equal to M plus N, and earlier we let here dimension of T is equal to M. Now we have to show that the dimension of MT is equal to N. Then we can write dimension of T plus dimension of MT is equal to dimension of V. For proving this, we claim here that T of V1, T of V2, T of Vn as a basis of MT, where V1, V2, Vn taken from this set, this extended element of the basis of V. To prove this is the basis of MT, we must prove two things. that this set is linearly independent, and another, this set span empty. So our first target to prove linearly independent. Let alpha 1 T of V1 plus alpha 2 T of V2 to alpha n T of Vn is equal to theta. And T of alpha 1 V1 plus T of alpha 2 V2 plus T of alpha n Vn is equal to theta, because T is a linear mapping, and by the linearity property of T we can write T of alpha 1 V1 alpha 2 V2 to alpha n Vn is equal to theta. And from the definition of curve T we see that because its image is theta, we see that alpha 1 V1 to alpha 2 V2 to alpha n Vn belongs to curve T. And since this element belongs to curve T, so we must write this element as a linear combination of basis of curve T. So we can write the element as alpha 1 V1 to alpha n Vn is equal to beta 1 x1 to beta n xn, beta m xn, sorry. And taking in one side all the element, we get beta 1 x1 plus beta m xm minus alpha 1 v1 minus alpha n vn is equal to 0. And this is the linear combination of x1, x2, xm to v1, v2, vn. And since this set is a basis of v, so it must be linearly independent. So by the property of basis of v, we can write beta 1, beta 2 to beta m is equal to 0, and alpha 1, alpha 2 to alpha n is equal to 0. And since alpha 1, alpha 2, alpha n is equal to 0, so from this relation we say that T of v1, T of v2 to T of vn must be linearly independent. So we see that this set of vector is linearly independent. Now our second target is, this is the span of empty. To see this, we take any element T of v from empty. T of v from empty. And since T of v from empty, then we must have v from v. And since v is a vector of v, then v can be written as a1 x1 to a m xm plus b1 v1 to bn vn, because x1 x2 xn b1 b2 bn be a basis of v. Now taking the linear mapping both sides, we get T of v is equal to this, and this is a1 T of x1 to am T of xm plus b1 T of v1 to bn T of vn. Now x1 to xm, these are x1, x2 to xm, these are, or this set is a basis of curve T. So these vectors belongs to the basis of curve T, belongs to curve T, and since these are from curve T, so T of x1 is equal to theta. Similarly, T of xm is equal to theta. Then putting this relation, we get T of v is equal to B1 T of V1 to Bn T of Vn. And this relation shows that any element T of V from empty can be expressed as T of V1, T of V2, T of Vn. So we say that this set is span the empty. So two conditions, linearly independent and span of empty. So we say that this is a basis of empty. And since this is a basis of empty and it consists n element, hence the dimension of empty is equal to n. Also we first let dimension of RT is equal to m. So dimension of empty plus dimension of RT is equal to dimension of V, because this is m plus m. And this proves the rank nullity theorem or Sylvester's law. Please give your valuable comment to improve my class and also to clear your doubt. Please stay with me. Thank you very much.